right, everyone. So we're going to begin session C for Group C. And again, please, can you stand up, Group C members? A round of applause to them, please. Okay. Thank you so much. All right, please be seated. So now I'm going to pass the mic to the chairpersons to begin the session.
All right. Good afternoon, everyone. Respected professors and my fellow global friends. Welcome again to ISS 25th. I hope you all have a great lunch and ready for the second session for today. So first, let me introduce ourselves. My name is Dewi and my partner is Yuki, and we are from Tokyo NODAI, now representing as a chairperson for Group C. So next, I would like to introduce my fellow members from Group C. First is Gabriela from University of Sao Paulo. Please give her applause. Second is Deep from Vietnam National University of Agriculture, Vietnam. And third is Martin from Sokain University of Agriculture, Tanzania. And last from Alia from University of Putra Malaysia, Malaysia. So I would like to remind again about the rule for today. So the presentation takes 12 minutes and question and answer is 3 minutes. So if you want to ask question, please raise your hand and mention your name and institution. And please make sure your question is clear and easy to understand. So without any further ado, let me invite our first speakers to present her activities. Gabriela from Brazil with the title is Microbiology Analysis of Milk from Small-Scale Producers, an inclusive activity for expanding access to nutritious food. So Gabriela, time is yours.
Good afternoon, everyone. I'm Gabriela. I'm an agriculture student at Luiz Queiroz College of Agriculture at the University of São Paulo in Brazil. And under the supervision of Professor Luiz Leman Coutinho, I developed this project called Microbiological Analysis of Milk from Small-Scale Producers, which I'm very glad to present to you today. So the consumption of fresh foods has been declining in Brazil and worldwide, being progressively replaced by ultra-processed foods, which are widely associated with public health issues, such as cardiovascular diseases, diabetes, and obesity. A recent study showed that in Brazil, a key factor for the consumption of fresh products is living closer to establishments that sell this type of product. The problem is that this type of establishments are usually on the central areas. So people who live on the outskirts in low-income areas have limited access to fresh products. In this sense, small peri-urban productions are a powerful tool in expanding the access of fresh products in those low-income communities. Yet, those small producers face some pressures, primarily because of the urban expansion and the industrial agriculture model, which has broader access to scientific resources, financial resources, technology, and rural credit, creating an uneven competition because they can offer better productivity at lower relative prices. In this sense, activities that promote access to scientific knowledge helps to strengthen local food production and expand the viability of fresh products in these communities. In this context, we chose to analyze milk production because both milk production and consumption are really relevant in Brazil. Milk production accounts for about 15% of the total value of Brazilian livestock farming, and over half of Brazilian dairy farms has less than 20 cows, being considered small properties. The consumption of milk is actually rising in Brazil. In 2024, it reached 178 liters per person. And finally, milk pricing is related to its chemical and biological quality, which is directly influenced by its microbiology. So how does the microbiome affect milk production? We can divide the bacteria we find in milk into three major groups. The first one being those that causes heart diseases, most especially mastitis. This type of bacteria diverts the energy from milk synthesis to immune response. There are also the fermentative microorganisms that can cause change in aroma and flavor, which can be undesirable and reduce the commercial value of milk. There are also the pathogenic bacteria, those that cause harms for the consumer. All this type of bacteria reduce food availability, cause economic losses for producers, and overall inefficient use of natural resources because the energy of the system is not converted into food production in its full potential. So with these demands in mind, we created this project with the objective to characterize small-scale milk production through integrated field observations and microbiological analysis, generating evidence-based recommendations to achieve a better microbiome profile and a better production, expanding the availability of fresh and nutritious products in the communities. So this project was carried out by 2 undergraduate students between 2024 and 2025. We collaborated with 2 small family-owned farms with about 20 animals each, and located in Piracicaba, Brazil. Piracicaba is a medium to small city in a traditional agriculture area, but the rural area has been receding due to urban expansion and industrialization. So students took part in every step of the project, from the engagement with producers, where we did some interviews about their practices and their demands, and observed their management practices, to laboratory analysis, so DNA extraction, amplification, sequencing, to bioinformatic analysis, to finally the correlation between the microbiome profile, the observed management practices, and scientific literature. They were used to create a good practice guide that were handed to producers. In this way, this workflow worked as a full circle because it both starts and ends with the contact with those producers, showing the inclusive nature of this project. So with all this analysis, which bacteria were we able to find in the samples? Here are 5 of the samples we have analyzed and the 6 most abundant bacterial genera. And what does the presence of this bacteria inform to us? As you can see, these bacteria are commonly found in various surfaces, suggesting various sources of contamination, which relates to what we observed, because they had like poor hygiene, which contributes to this contamination profile. And analyzing the effect that this bacteria has on milk, we can see that the first one, Acinetobacter, is some species of this genus can cause opportunistic infections, but the other ones are mostly fine, except for lactobacillus and lactococcus that are fermentative and can create undesirable sensory changes, which, as I said before, reduces the commercial value of milk. Other than the most abundant ones, we are able to find some relevant bacteria, such as Enterococcus, that is heat resistant, and some species can also cause opportunistic infections. Klebsiella, that causes mastitis, which, as I said before, reduces both quality and quantity of production. Cocuria, that is found in animal skin, suggesting the source of contamination, probably because the dairy cows had contact with other animals, which we observed. And Clostridium, that is also a heat-resistant bacteria, but associated with a lower shelf life. With all this information and scientific literature, we developed a good practice guide that you're able to read through scanning this QR code. We have summarized and made accessible all this information, so producers could really understand why it is important to know about microbial contamination and suggested low-cost practical actions to be able to achieve a better microbiome profile and overall production, which created a higher producer engagement because it was a direct response to what we observed and what they told us as demands. So we really could um, see some transformations in their practices, creating a better microbiome profile and better productivity after all, and better income. The major challenge we faced was the initial distrust from producers, since they feared that the data we collected could be used for regulatory enforcement. We are able to overcome this by the frequent contact with those producers, which created a more trustful relationship where they were more open and honest to talk about their practices. Yet, it limited the number of producers we are able to collaborate with. Our major perspective is to strengthen local food production and expand the viability of fresh and nutritious foods in the communities. We also expect to improve resource efficiency by both reducing production losses and also by offering a shorter distribution chains, which reduce pollutant emissions. And finally, we expect to inspire similar initiatives from other students from other regions, so we could have a broader data set and more efficient recommendations. So in conclusion, how does this project align with the theme of the 25th ISS? This project pushes boundaries by translating advanced and often accessible technologies, such as DNA sequencing, into an inclusive initiative that promotes community welfare, strengthens local food production, improves access to fresh, healthy, and nutritious foods, and enhances the energy efficiency of local food systems. I would like to thank my colleague, Gabriel Santana, which collaborated with me in this project, all my colleagues from the Applied Genetics Club, and my supervisor, Luiz Coutinho. And you all for your attention. Thank you very much. Arigatou gozaimasu. Muito obrigada.
Thank you, Gabriela, for your presentation. Let's give her one more big applause. So from her presentation, we understand that microbiology in the milk production and the output of her activity is a good farming practice for the milk producers in Brazil. So based on that, now we open a Q&A session. Are there any questions or comments from the audience? Yes, please.
Thank you for your presentation. My name is Toki. I am a student from this university, Tokyo NODAI. So my question is that what kind of institutional support or policy do you think which can help farmers to maintain this microbiological quality in the long run? Thank you.
Thank you for your question. Based on our observations, the major problem that the producers faced is the activity doesn't offer enough income for them to invest in such infrastructure that could provide a better microbiome profile. So one major policy that could be taken would be some kinds of an easier rural credit for them to really invest in their infrastructure and achieve this better microbiome profile. So yeah, in Brazil, the rural credit policy is very difficult for small producers to access. So this would be like the major change that would allow producers to have a overall better productivity and better microbiome profile. Thank you.
Thank you.
All right. So any other question? So I have a question. So how are you planning to share the output of your activities, such as a good practice, to other milk producers in Brazil?
Yeah, we already shared with those producers that collaborated with the project, but we are also sharing this information online through my club Instagram. This project was a part of a collaborative project from the Applied Genomics Club that I take part in my university. And we like share this information via Instagram, so it could reach like a broader audience. And we also participate in some events showing that these results and showing how they can achieve this better profile.
Okay, thank you very much. And any more question from audience? Okay, if not, I have another question. So I want to know, like, how are you like identify this microbiology? Like, how what step did you do from the milk producer to laboratory? Like, did you do sequencing or how do you do your steps?
Yeah, we used DNA sequencing.
Okay.
So like next generation sequencing, we actually like it's kind of hard to extract DNA from milk because milk has so much fat that is a little difficult to get the DNA, like to get a good read of its sequencing. But we are able to, like, we needed to test so much times, but at the end we are able to do this, and we analyze the microbiome profile using DNA sequencing.
All right, thank you very much. Any questions or comments? All right.
I'm just interested. Hello, I'm Vasin Sarforn from Kasetsart University. I'm just interested to know from the guidelines that you have put together, is there any parts of the guideline that you observed and saw that it did not overlap with current guidelines in milk production?
Thank you for your question. I mean, almost no guidelines are like new things, but we saw that producers didn't adopt this practice because they felt like it was very institutional and not like made for them. So there's no new guidelines. They all like are very similar to the existent ones, but the really innovation of this project was to offer a response, like to hear from producers and then talk to them. The innovation of this project is the inclusive part of it.
Oh, I see. Thank you very much.
Okay, so time is up. Thank you very much for all your attention, and let's give her one more big applause. So the next presenter, I'm inviting Zeep with her presentation topic is Youth Drivers Genetic Mapping for Pre-Harvest Protein Resistance, Building Climate Resilient Rice System in Central Vietnam. So Zeep, floor is yours.
Xin chào mọi người. Hello everyone. My name is Chen Big Diep. I'm honored to be here to represent our research team from Vietnam National University of Agriculture under the supervision of Dr. Nguyễn Quốc Trung. And our project entitled Young Driver Genetic Mapping for Pre-Harvest Protein Resistant, like Building Climate Resilient Rice System in Central Vietnam. This project will approach to compile with the genetic molecular genetics combined with the young participation and community engagement to can provide a practical solution to the climate related to challenge in the rice production. Yes, and rice is not a staple food in central Vietnam, but also a primary source for the livelihood of millions of family households. And central Vietnam, Central that there is the Central Vietnam is the particularly 13 Hue province. 13 Hue province is red point here. The price that not only the country important rice production region is, however, the region is becoming risky, vulnerable to climate change. So the harvest region often overlap with the periods of heavy rainfall and flooding. For example, in 2020, more than 60,000 hectares of rice field experienced pre-harvest sprouting. And now I have a picture to compare the difference between the rice germination between the in normal condition and the when the stress climate stress. You can look at the normal condition. Because the normal condition, under the normal condition, the rice rain remains the domain with the harvest, and is only generates after planting. But in climate change, this climate change, under climate change, the seed dormancy is disrupted, and as a result, that rain begin to germinate directly on the panic before the harvest, and this lead to the pre-harvest sprouting of PSS. PSS is the premature rain germination before the harvest, and this occur when because the excessive moisture disrupt the seed dormancy. And normally, seed dormancy is regular by the balance between the two important plant hormone like acetylsalicylic acid ABA or glycolic acid EGA. And PSS occurs like I mentioned in the below that PSS occurs because the excessive moisture disrupts the domains, and it under the prolonged condition, ABA level decrease while GA activity increase. There's a called the phenomenon reduce the rain quality and lower meeting performance and decrease market values. Therefore, developing rice variety with a stronger resistance to harvest has become an urgent priority to climate resilient agriculture. And to address this challenge, our student team conduct an integrated research project in Hue City, a flat for rice growing area in central Vietnam. Our research team evaluate two promised rice like is PSR7 and PSR8. And we also use KD18 US cultural variety, and is conducted by the student from my university with the support from my supervisor, my family, and local stakeholder. And firstly, we began in the laboratory research. We will perform some molecular biology technique like quill tail mapping in laboratory to identify the genomic reason associated with resistance to pre-harvest sprouting. Is based on the molecular marker, and we will select to promise the rice line. Next, the rice lines we are all evaluate in the farmer management by in a few trial under the natural flood flow condition in Hue City. And during the field experiment, we also assess it grain yield, plant performance, and resistance to PHS. Finally, we have some organize the some community engagement activity that brought students and local farm to demonstrate the performance of resistant wildlife, share the scientific knowledge on PHS and exchange practical experience for climate resistant rice production. And as well as in the table, you can see that the both PSR 7 and PSR 8 have achieved the performed local variety KD 18. Regarding the grain yield, KD 80 products only 1.2 tons per hectare, but in PSR 7 and PSR 8 up to 1 ton per hectare. As even more significant that the improvement that was observed in the PHR resistance, you can see that the resistance in PSR 7 and PSR 8 is more than double than local variety. And this means that PSR 7 and PSR 8 still combine to both the high productivity and strong resistance. And this finding clearly demonstrate that quail based on the selection successful improve both the grain yield and the resistance simultaneously, which is particularly important for the beating climate resilient rice variety. And we also have a picture the sort of phenotypic the performance of PSR 7 and PSR 8, and the field they observe the further to confirm the quantity result. And as you saw the picture of the PSR 7 and PSR 8 meant healthy plants architecture and so the very limited pre-harvest sprouting under the field condition. This candidate that resistant identified through molecular analysis remain stable under real agriculture environments. And from agriculture's perspective, stable field performance is particularly important because the farmer needs variety that combine the high yield and strong resistance and good adaptability under the unpredictable weather condition. Therefore, this rely have a strong potential for the further cultivation in the flood flow region of central Vietnam. Despite all we have many encouraged results, we encountered several challenges during this project, like quail mapping with and we need required advanced laboratory facilities and stable financial support. So it's very, very hard for the student project. And some farmers either intentionally hesitant to adopt a new rice life because they're concerned about the market acceptance and also like the yield stability. And in addition that in Quay City, we have extremely weather. Then this occasionally affect on the field experiment and we can control. So although some limitation, our finding this demonstrates a strong potential for further application. We believe that expanding field variation through collaboration with local farmer breeding program and agriculture extension service will facilitate to adoption of climate resilient rice variety in vulnerable rice region. And conclusion, our project validates that molecular genetic can provide actively solution to the climate related to agriculture challenge. We successfully identified promoting the right fly, and more important that our project connect with the laboratory research with the community engagement, active to of student like student, local farmer, and this project is fully the allied with the ISS terminal, the pushing bodies inclusive activity for community welfare. As a young research, we believe that the scientific innovation shouldn't remain inside laboratories. Inside it should create the real benefits for framing communities and contribute to the sustainable and climate resilient agriculture. We hope that our work will inspire the more the younger to use the science as a tool for the addressing the global challenge. And thank you for your attention. Xin chân thành cảm ơn ạ.
Thank you, Deep, for your presentation. So from her presentation, we understand there is an emerging variety of rice, which is PSR and PSR8, that have resistance for flood-prone condition that been modified with the molecular genetics. So we are opening for question and answer. Is there any question, comments? Yes, please.
I am Khalid from Bangladesh Agriculture University, Bangladesh. So thank you for presenting in molecular genetics field. It was nice. I want to just know that how many varieties did you test?
You can speak slowly so I can.
Okay. How many varieties did you test?
Depend. How? That's it. Variety. How do it variety?
How many number the variety did you test?
We use two variety because each variety we cultivate a lot of like about maybe it's about 500 plants for one variety.
Okay, thank you.
Yes.
Thank you very much. Any other question or comments? Yes, please.
Thank you for your questions. My name is Sukrita from Thailand. So I have a question for this study. You trial already, right? So I would like to know about type of photo period of your plants and how many days we can harvesting. Yeah, that's my question.
Okay, you want to know about the time of my picture?
I mean, photo period. That's type of your fixed breeding lines.
So for she's asking for PSR7 or PSR8, how long that they can be harvested?
Yes, yes.
So we have a plant this we waste maybe nearly 1 year.
You're developing for 1 year,
Yes.
and then development from growing until harvesting, how many times?
From look by you between from the seeds, yeah, and until it become the plant trees like this. It weighs 1 year.
Oh, 1 year. So after 1 year, then you can harvest.
Yes.
Ah, okay. So is it enough?
Also, like, I mean, it's like, how many days we can harvesting rice, and since you planting and time to harvest, how many days? Life cycle.
Yes. Actually, I'm mainly doing the research in the laboratory. I'm always, and so I don't clearly about the days, but from my finger, I received from the local farmer is about six, 65, no, sorry, 65 days. 65 days to 70 days. Around this.
I think this project is very good for me. And if you can tell me actually about the days that we harvest, maybe we can avoid to the flooding that you talked earlier in problem. So that like a farmer, we can harvesting before flooding or before have rainy that day. Yeah, thank you so much.
Yes, thank you so much.
Okay, thank you very much. Because of time is up. So thank you very much, Deep. Let's give her one more big applause. All right. So for our next presenter will be introduced by my chairperson partner.
Our third presenter, Martin Harry Kawago from Sokoine University of Agriculture in Tanzania, will introduce the potential use of banana peels and banana bunch as a construction material for resource recovery. This presentation focuses on how agricultural waste can be transformed into valuable construction materials, contributing to environmental sustainability and resource recovery. It shows that innovative ideas can turn everyday waste into practical solutions for both communities and the environment. Please join me in welcoming our third presenter. Martin, the floor is yours.
Distinguished guests, professors, chairmen, my fellow delegates, ladies and gentlemen, good afternoon. My name is Martin Henry. I'm from Tanzania, and I'll be representing Sokoine University of Agriculture. I am here to present my research title that's titled The Potential Use of Banana Peels and Banana Bunch as a Construction Material for Resource Recovery. Before carrying on, I would like to ask you a simple question. Do you know the banana? Any person who don't know the banana? Your hand up. Okay, well, I thought there's a person who don't know the banana. I came with it as an example. Oh, thank you. Okay. Tanzania, it's one among the largest producers of bananas in the world. It's among the best African producers of banana peels, the banana production. According to the UN, the UN data analysis in 2024, it said that the urban population it's growing high. So in countries like Tanzania, maybe there are a lot of people who are eating this banana. It's like a staple food in my country. So most of the banana peels, once they are eaten, they are rooted down. The problem that I encountered during my project, it was there are a large amount of the banana peels and waste that are littered in our environment, and also there is a high demand of low construction material. These are the two major problems that we faced. So we found this project like it's the most good way that we can face it. This one, it's an example of the banana peels that are littered, they are thrown in the local markets maybe. And this picture was taken in the local market in Mbagara district in Tanzania. Me and my team, we managed to perform the following activities that we managed to promote the community welfare by cleaning the environment, by collecting the waste of the banana peels, and we managed to dry them, and we cleaned them and washed them ready for our project. In which in our project we managed to, we conducted, it was the laboratory tests in which we took the banana peels and we grinded them into fine powder, in which this fine powder, it's going to be used like a replacement for the cement, the Portland cement. This one is one of the activities in which this one is the banana and this one are the peels. And here it's when we dried it and we grinded it and we managed to make the final powder, in which it's like 9% of the cement that we are going to use it in a construction of a normal concrete. We are going to replace it by 9%, and it will be used for making a concrete. The best approach is just because this banana powder, it has a binding energy, just like cement. And here we managed to make the implications, like the difference between the normal concrete and the concrete made from the banana peels and bunches powder, in which the only difference, it's here, I mean, in the preparation stage. In the preparation stage, like you can see, there are other material inputs, like we use the cement, we collected, we washed the powder sun drying, and we grinded into fine powder. And the other steps were just like the same, like the normal concrete, in which in the normal concrete, we use only the Portland cement, sand, coarse aggregate. Yeah, and we dried, then we waited and casted them and into vibration, like pressing them into the molds that you want, the shape of the concrete that you wanted. And this one is the picture of a normal concrete. And this one is a concrete that's made with 9% of the banana powder and peels. This one also is one of the picture of the banana concrete made. It's like it has a good looking in terms of appearance compared to the normal concrete. So it's more attractive in terms of looking. And this one, it's the normal concrete, it's just white. In this picture also, this one is the concrete that shows how eco-friendly environment. Like it promotes the environment from being dirty to a clean environment. The major challenges that we faced here, it's the variability in the banana waste which affect the consistency of the brick production. Like we can know that in all seasons that the production of these wastes made from the banana peels will be the same. But in the other seasons, there will be high production of this waste, but in other seasons, there won't be production of this waste. Also, it's a limited technology, like on the processing methods, and also lack of standardized procedures and inadequate testing facilities due to the bulk technology. Also, the other problem that we faced, how can we make the stakeholders aware of this technology, because most of the stakeholders are not aware of this technology. So we need to advise them how to use this kind of technology so that they can invest in our technology that we have implemented. Lastly, by finalizing our conclusion, we managed to find that the use of the banana peels and banana bunch have led to the reduction of the environmental waste. So it quickly aligns with our theme that is pushing boundaries. Yeah, and it's in terms of community welfare, it reduces since there is a reduction of the cost of the banana bricks. The banana bricks construction cost is too low compared to the normal concrete. So it can push up our community welfare in that teams. Lastly, finalizing, I would like to extend my gratitude to my academic advisor, Dr. Nsenga, and my academic supervisor, Dr. Nelson, all the way from Tanzania. Also, I would like to thank the ISS team for this opportunity. Thank you. Asante sana.
Thank you, Martin, for your insightful presentation. We understand that agricultural waste can become a valuable resource when combined with innovation. By recovering and reusing natural materials, we can reduce environmental impacts while creating sustainable and affordable solutions for our communities. So we will now move on to the Q&A session. Does anyone have questions or comments? Yes, please.
Thank you. My name is Hunter Ogochi, student at Tokyo NODAI. Thank you, Mr. Henry Kawago, for your wonderful presentation. I have one question regarding the type of banana grown in Tanzania. Is it one cultivar being used as waste, or it's different varieties of banana being used for the waste production? Thank you.
Okay, thank you. Thank you for your nice question. According to our research, we based on this kind of banana, not one, the small ones. We based on this kind. It was only this kind.
Thank you.
Welcome.
I'm Vasin Sarapurn from Kasetsart University. Thank you very much for the, I think that your idea is very innovative and very sustainable. It's very interesting. I just want to learn more about the strength of the bricks from the banana compared to conventional or the bricks that we're currently using. Is it comparable, or I would like to hear your ideas on that,
Yeah.
please.
Thank you for your nice question. I would like to explain it as follows. It was the concrete that's made from, the normal Portland cement, the sand and aggregates. Their compatible strengths, it's almost like 20 MPa. But the ones that it's made from the banana peels and bunch powder, it's like 16 MPa. That's a standard. It's too standard, yeah.
So in your opinion, do you think it could one day perhaps, if it were to be produced in mass, could it perhaps replace the bricks we currently use?
Yeah, exactly. It's too promising. It's like, because when it's for the, the minimum construction bricks. There are 3 types of bricks. It's the minimum that's used to make, the normal buildings, and the standard bricks. Yeah. So for the minimum bricks, it's good. It's more good and more promising.
Oh, wow. Thank you very much.
Thank you. Any other questions? Any other questions? Please.
Thank you for your good presentation. My name is Joe
Thank you.
Nyarimba from Tokyo NODAI. I'm
Welcome.
wondering, for the bricks, you are focused more on the urban areas. Are you going to include the most vulnerable groups, like people from the rural areas, for this kind of a project to have some inclusive activities?
Thank you for a nice question. According to our project, we started with the local farmers in the rural areas. Yeah. Then we extended it into, the urban areas too, because in the urban areas, there's a high population compared to the rural areas. So we began with the local farmers who are planting the bananas. Then we extended it to the urban areas. Yeah.
Thank you for your questions.
Thank you for your presentation. My name is Anand Nakajima from Tokyo University of Agriculture. And my question is a bit similar to what he said, but I just wanted to know the bricks of how much years can it hold, and if it's vulnerable to rain and water. I think the concrete could last about 45 through 70 years, but can it last that much? And in Japan, it's usually have earthquakes, but I think wanting to know it can build something like that, close to that. Is that okay?
Yeah. Thank you for your nice question. According to our research, we just began it. It was we made it. It was for only 28 days. It was like the curing stage. It was the same curing stage of the normal concrete, but we haven't yet made it. I mean, to determine how long, because we just began it. It's like we haven't even made it to 10 years. Like it's just beginning, but it seems so promising. Yeah.
Thank you.
Thank you, Martin, and the audience. Again, let's give Martin a round of applause. So now let's move on to our next presentation. Our fourth and final presenter, Kamsum Alia binti Abdul Hadi from the University of Putra Malaysia, will speak on From University to Community, Food Science and Technology through the Practical Workshop. This presentation highlights the importance of education and community engagement in promoting food science and sustainable practices. By sharing knowledge through hands-on learning, students can inspire future generations and strengthen connections between universities and local communities. Please welcome our final presenter. Alia, the floor is yours. Please.
Thank you, Yuki. Before I begin, I would like to ask all of you a question. How many of us truly understand the science behind the food that we eat every day? Most of us consume food without understanding this, how product is evaluated, how science ensure that the food is safe for consumption. Yet, a single mistake in food handling can have serious consequences for public health. This concern became even more apparent as Malaysia continued to report food poisoning incidents involving school communities. These cases remind us that food safety is not only the responsibility of food handlers and manufacturers, but also a generation that is knowledgeable, aware, and scientifically literate on food science. As highlighted by Dr. Salini Ravensrand in one of Malaysia's famous news, there is an urgent need to strengthen food safety education among young people. This raises an important question. How can we make food science more accessible and meaningful to the school community? Today, I would like to present how our project attempted to answer that question through practical, hands-on food science workshop. Good afternoon, konnichiwa, and selamat petang. My name is Kamsum Alia binti Abdul Hadi. You can call me Alia shortly. I am from University Putra Malaysia, and my supervisor is Dr. Nur Afizah binti Mustafa. Today, I am pleased to present our project entitled From University to Community, Food Science and Technology through the Practical Workshop. Food security and sustainable food production are major concerns in Malaysia. In addition, food safety issues remain serious, especially in school settings. While food handlers play a critical role in ensuring safe food preparation, students are equally important as they represent the future food practitioners and consumers. Early education helps build long-term awareness and preventive behavior toward food safety. For example, in 2024, food poisoning incidents have shown that poor hygiene and unsafe food handling can affect students and school communities. This highlights the need for better food science education and stronger awareness of safe food practices. At the same time, many students have limited hands-on exposure to food science concepts. As a result, interest in STEM may decrease. STEM stands for Science, Technology, Engineering, and Mathematics. The workshop is directly related to STEM because it combines theory with hands-on practice, practical processing, and analytical testing. In food science, students do not just learn concept from books, but they also apply science and equipment, solve processing problems, and evaluate product quality. Therefore, there is the need for accessible learning programs that connect universities with school communities. Every fifth semester, students in Bachelor Science of Food Manufacturing Operation, which is my course, are required to organize 2 community programs for plant manufacturing product and animal manufacturing product. The objectives of this workshop is to bridge academic knowledge and community learning through inclusive, hands-on food science education. We also aim to increase awareness of food safety, food processing, and sustainable food production through these student-led STEM outreach programs. Our programs activities brought the university and school communities to practical setting. The idea was to let participants learn food science through direct experience using the high-tech facilities available at the university. We also aim to this created a meaningful learning environment where theory could be linked into practice. As one of Malaysia's leading universities in food science and agriculture, UPM provided participants with the opportunity to experience authentic laboratory environments and industry relevant equipment that are not commonly accessible in school settings. This timeline illustrates the continuity of our engagement initiative since its introduction in 2022. Over the years, students have organized a series of food science workshops, each focusing on different aspects of food processing and product development. The journey began in 2022 with noodle making workshop, and then followed by HPP pineapple juice workshop in 2023, continued by smoked chicken workshop in 2024, followed by soy workshop in 2024 also. And then in 2025, we have mango to puree workshop, patty burger workshop, and recently we have noodle making workshop. The picture of the machine here are the main highlight of the program. Each year or each workshop highlight different types of machine that we want to teach the school students. In 2024, on this project, I served as the director of the soy workshop named as Soy So Happy, which is a hands-on tofu making workshop. Tofu was chosen because it is widely consumed, affordable protein source, supports healthier eating habits, and relevant to food science education. This is the brochure that we gave to the students. Okay. For the student activities, the workshop began with an introduction to food science and processing concepts in the hall of auditorium. And then we bring the school students to our laboratory. The facilitators will demonstrate how the machine used and the effect to the food processing, how it elongates shelf life, and so on. After that, the students will have a hands-on practical session by themselves, and then continued by analytical testing and quality evaluation, like pH, Briggs test, and also sensory evaluation. After that, students will have interactive quiz and discussion to see their understanding of the workshop. And lastly, we have reflection and feedback session. For the implications, this workshop improve high school students' understanding of food processing, food safety, and product quality through hands-on learning. It also increased their scientific literacy and interest in food science and technology as possible career pathways. In addition, the workshop promoted sustainable and hygienic food processing practices using practical, low-cost, university-based resources. Most importantly, it demonstrated a replicable model for inclusive STEM outreach programs that supports community welfare and food system resilience. This means the workshop can be repeated and adapted for future outreach programs. For the challenges, we faced several challenges during implementation. Firstly, because of the limited lab space, restricted the number of participants. And secondly, limited equipment caused waiting time during activities. The one-day format also limited deeper learning. To overcome this, we use a station rotation system so that all students could still take part. For future workshops, a multi-day format and wider outreach can be considered to improve learning depth and community impact. In conclusion, this project demonstrates how university students can push educational boundaries by bringing food science beyond the classroom and into the community. Through this inclusive hands-on workshop, schools and local communities work together to improve food science awareness, food safety knowledge, and interest in STEM-related courses. This workshop also supports SDG 4 by providing inclusive hands-on learning that improves scientific literacy and encourages interest in STEM and food science. It also aligns with SDG 12 by promoting sustainable and hygienic food processing practices, efficient use of resources, and responsible production methods. In addition, it contributes to SDG 17 through strong collaboration between university students and community partners, showing how partnerships can create meaningful impact for community and food system resilience. The project demonstrates that food science education should not remain within university walls. By sharing knowledge through inclusive community engagement, we can inspire future generations, strengthen food safety awareness, and contribute to community welfare. This is how we push boundaries by transforming knowledge into impact. I hope this project gives all of you an idea to work with school community in your own universities. No matter whether the focus is on food, agriculture, or the environment. Thank you.
Thank you, Aliyah, for your presentation. We understand that education is one of the most powerful tools for creating sustainable communities. By sharing knowledge and engaging younger generations, we can spread awareness, inspire future innovation, and strengthen communities. So we will now move on to the Q&A session. Does anyone have questions or comments to Aliyah? Oh, yes, please.
Okay, thank you for your nice presentation. My name is Martha from Tokyo NODAI. Just out of curiosity, for the machines you highlighted that you used in your workshop or project, what's the direct connection with the quality or food safety at large? Like, how was the quality of the food that was made from the machines assured during the processing? Thank you.
Thank you, Mata, for the good question. So you asked about the machine, how it's related to food safety. When we explain to the students about the use of the machine, we also explain how the process affect the product quality, how it can prolong shelf life, how it could kill microbes and make the food safe for consumption. I hope that answered your question.
Okay, thank you.
Next question, please.
Good afternoon, everyone. My name is Anne Mudui from JKUAT, Kenya. My concern or my out of curiosity, I want to understand what causes the food poisoning. I haven't gotten the connection between the food poisoning and your presentation. Thank you.
Thank you, Anne, for the good question. Like I've mentioned before, food poisoning is not only the responsibility of food handlers or manufacturers, but also a generation that is knowledgeable, aware, and scientifically literate on food science, because they are the future food handlers. So we want to educate this generation to have a preventive behavior towards our future. I hope it answered your question.
Thank you so much, Aliyah, and the audience. So let's give her a round of applause. So Aliyah, you can have a seat again. All right, to wrap up our session, I would like to highlight a few key takeaways. We have learned that although each project approached a different challenge in different fields, they all share the same goal: improving community welfare through innovative and inclusive activities. The first presentation showed us how scientific research can improve food quality and support local dairy producers. The second demonstrated how genetics and collaboration can strengthen climate-resilient food production. The third reminded us that agricultural waste can become valuable resources through creative thinking, while the fourth emphasized that education and knowledge sharing are essential for building sustainable communities. Together, these presentations highlight that science, innovation, education, and collaboration are all interconnected. Sustainable solutions are not created by technology alone. They are achieved when researchers, students, producers, and local communities work together. As young researchers and future leaders, we all have the opportunity to push boundaries, share knowledge, and create practical solutions that contribute to more resilient food systems and a more sustainable future. We would like to express our sincere appreciation to all of our presenters for sharing their inspiring work, and thank you to everyone for your participation and thoughtful attention. Please join me in giving all of our presenters a big round of applause. Once again, thank you very much, and we hope you enjoy the rest of the International Student Summit.